So welcome back to this next video in the playlist on Galois theory. In the previous three videos on radical extensions and then solvability by radicals and then the one on the non-existence of the quintic formula, we have proven that in any characteristic zero field there will not exist a quintic formula, and indeed a formula for the roots of general polynomials of higher degree either. Except we only prove that if you assume a certain lemma, and that lemma that we stated, used, but didn't prove was that for characteristic zero fields, any radical extension is always contained inside a finite solvable extension, and any finite solvable extension is always contained inside a radical extension. We now need to go back and prove this, and I said at the time when we used it that it takes some effort to prove that, and then really this is the hard bit of this famous proof. We've done the bit that comes afterwards, which is kind of the fun bit, and now we need to go back and do the more boring and harder bit. So towards that, the two key ingredients that go into these proofs are you need to understand Kummer extensions extremely well, and you need to understand cyclotomic extensions quite well as well. Once you understand those two things well, we can then prove these two results. So this video is therefore going to be on Kummer extensions, and the next video will be on cyclotomic extensions, and then after we've done that, we'll then have two videos dedicated to proving each of the two results. So Kummer extensions then is the topic for this video. So I'm going to firstly define what a Kummer extension is, then we'll prove an equivalent definition of a Kummer extension, and then we'll take it a little bit further still to kind of give another way of constructing Kummer extensions, which is going to be the most useful. So again, this definition actually holds not just for characteristic zero fields, but for general characteristic fields. So again, we'll do it in full generality just so that you can see it in its generality, but of course we'll just be using it for characteristic zero fields. So a Kummer extension then, so let's say you have a base field f, and you have some extension k, and k is going to be the Kummer extension, but it's going to need to meet certain criteria to be a Kummer extension. And let's say that this extension has degree n, where n is some natural number, not 1 of course, it will need to be bigger than 1. And let's say the trivial one, if you like, you can count it as a Kummer extension trivially, but it's not the spirit of the idea of a Kummer extension. And the base field needs to contain a primitive nth root of unity, which I'll denote zeta n. So what do I mean by a primitive nth root of unity? So remember, we're not necessarily talking about the complex numbers anymore, so zeta n doesn't necessarily mean e to the 2 pi I divided by n anymore. So what it means in this context is it means some element in the field which, if you raise it to the power of n, you get 1, so that's being an nth root of unity. This is the definition of being an nth root of unity. Being a primitive nth root of unity means that if you raise it to any smaller power, so if you do it to the power of any natural number, so if I replace up here the exponent with any natural number that's smaller than n, that it doesn't equal 1. So raising the element to the power of n gives you 1, that makes it an nth root of unity. To be a primitive nth root of unity, it has to be the case that that is the smallest power, apart from 0 of course, but the smallest natural number power, where we're taking the natural numbers to not include 0, which actually gives 1. So all the smaller powers don't give 1. So it's not a smaller nth root of unity. Now, this immediately means if the ground field contains a primitive nth root of unity, it immediately means that the characteristic of the field, so characteristic of f, does not divide n, because if it did, so let's say if the characteristic was some p, so we don't have this problem in characteristic 0, but if the field had some finite characteristic, let's say it had characteristic p, and the characteristic did divide n, so n was equal to some power of p to the power of alpha, times m, where m is some other natural number that doesn't doesn't have p in its prime factorization, so p doesn't divide m. So this is what n is equal to. So literally I'm just splitting n into the power of p, and then what's left in its prime factorization, which I'm calling n. So if n was like this, so if the characteristic of the field is p and p does divide n, the problem you get is that that field can't contain a primitive nth root of unity, because if it did, it would be a solution to the equation x to the n minus 1 is equal to 0, so it would be a root of this polynomial. But the problem is that that polynomial is x to the p alpha m minus 1, so I've just substituted in n is equal to p to the alpha times n, and now this factorizes in characteristic p to x to the m minus 1 to the power of p to the alpha, because if you expand this in characteristic p, it's just going to give exactly this. So this is a problem, because it means that any root of this original equation is going to now be a root of this inner equation here, this inner polynomial here. So it'll be a root of x to the m minus 1 is equal to 0, and therefore it will be an nth root of unity. So any nth root of unity, so if it's an nth root of unity, it immediately implies it's an nth root of unity, which then means it's not a primitive nth root of unity. So this proves basically that if you're in a field with characteristic p and p divides your n, then there won't exist any primitive nth roots of unity in that field. So it therefore has to be the case, if the ground field contains a primitive nth root of unity, that the characteristic of the field does not divide n. Right? So back to the definition then of a Kummer extension. So we have this extension of degree n where the base field contains a primitive nth root of unity, and the field k, the extension, is the splitting field, and this is the definition then now of a Kummer extension. It's the splitting field over f of some polynomial of the form x to the n minus a, where x to the n minus a is an element of the irreducible polynomials in the ring of polynomials over the field f. So all this is saying is that you take some polynomial where this n is appearing again, so the degree of the extension, so you take some polynomial of the form x to the n minus a, where a is some element in the field f, and you want this polynomial to be irreducible over f, and then if you construct the splitting field of that, I need to prove to you that that will give you an extension of degree n. If you take a splitting field of a polynomial of this form over a base field that contains a primitive nth root of unity, such an extension is called a Kummer extension. So we're really, as you can see, adjoining on an nth root of this element a here in the base field f onto a base field that already contains a primitive nth root of unity. So the containment of the primitive nth root, so the containment of the primitive nth root of unity is very important. So let's just convince ourselves that this will give an extension of degree n then. So it's actually because the extension that you get is going to be a simple extension. So if you take a single root, let's say alpha, alpha, I know I've already used alpha down here, but forget this now, we're done with this bit down here about this. So alpha is now taking on a new meaning. So alpha, let's say, is an element of k, where I'm defining k to be the splitting field over f of this polynomial x to the n minus a, and we're going to say alpha is a root of the polynomial, so alpha to the power of n is equal to a, therefore. So my first claim, is that the field k is going to be achieved by just adjoining on alpha. It's going to be a simple extension achieved by joining on alpha. Why is that the case? Because once you've got alpha in there, because the ground field contains a primitive nth root of unity, you immediately are therefore going to contain alpha times zeta n. You're also going to contain alpha zeta n squared, all the way up to alpha zeta n to the n minus 1. And these are all different elements, these powers of zeta n, because if they weren't different elements, so for example, if you had zeta n to the 2 is equal to zeta n to the 3, we'll now just multiply through by zeta n to the negative 2, or zeta n squared inverse, and you'll get that 1 is equal to zeta n, which then contradicts zeta n being a primitive nth root of unity, because we've now got zeta n to the power of 1 is equal to 1. And it's supposed to be the case that no smaller power of zeta n, no smaller natural number power of zeta n gives 1. So yeah, none of these can be the same, because if any of them were the same, you could do a similar thing to here and get some smaller power of zeta n equaling 1, and contradicting the assumption that zeta n is a primitive nth root of unity. So all of these different powers of zeta n here, these are all different elements in the field, and therefore alpha times them gives different elements in the field. So overall, what we've got here, starting at alpha going down to alpha zeta n to the n minus 1, we've got n different elements of the field here, but absolutely all of them are now going to be roots of this polynomial here, because if you stick them into that polynomial, for example, if I take alpha zeta n to the I and I raise that to the power of n, that gives me alpha to the power of n, and then zeta n to the I to the power of n is the same as zeta n to the power of n to the power of I. Zeta n to the power of n is 1, so we've got 1 to the power of I, so it's just the same as alpha to the n. And then we know alpha satisfies the polynomial, so therefore alpha to the n minus a is equal to 0. So this basically shows you that all of these n distinct things that I've built here, they're all going to be roots of that polynomial. So once you've adjoined on one root of the polynomial, you immediately get them all, and therefore my field f adjoin alpha is indeed equal to the entire splitting field of the polynomial over f, and therefore is equal to k. Good, so it's a simple extension. Now, what's its degree therefore going to be? Its degree is going to be the degree of the minimal polynomial for alpha, but this is the minimal polynomial for alpha because it's a irreducible polynomial by assumption that is satisfied by alpha, and it's monic. That's the definition of a minimal polynomial. So this is the minimal polynomial for alpha. It has degree n. Therefore, the degree of f adjoint alpha over f is equal to n, and therefore this is all working quite nicely. So this is the definition then of a Kummer extension. You take a ground field f that contains a primitive nth root of unity, and you then create a splitting field of an irreducible polynomial of this form, x to the n minus a, which is irreducible in the ring of polynomials over the ground field f. Take the splitting field of that, and that's immediately guaranteed to have degree n, as I've just argued, and this type of extension that you've produced is then called a Kummer extension. So if you have an extension that's produced in this way, then you can call it a Kummer extension. Now, what I want to next show you is that Kummer extensions are actually cyclic extensions. So their Galois group is going to be Cn. So I want to show you that Galois group of k over f is isomorphic to Cn. So a cyclic extension, just in case you don't know, is a finite Galois extension where the Galois group is a cyclic group. So I want to prove that these Kummer extensions are all cyclic extensions, and indeed this is but then once we've done that, I'm going to show you that actually if you have a cyclic extension of degree n where the ground field contains a primitive nth root of unity, then you can immediately conclude that that's a Kummer extension. So that's another equivalent definition of a Kummer extension. So firstly, to try and convince us that the Galois group then of these Kummer extensions is equal to Cn. So we go back over here. We know that this extension is achieved by just adjoining on a single root of the polynomial. Therefore, understanding what the automorphisms of this extension are, or the f automorphisms of k are, is very simple. They're completely and utterly determined by where you send this element alpha. So I just need to tell you where you send the element alpha. And alpha is going to have to go to another root of its minimal polynomial. So it's going to have to go to another root of x to the n minus a. So it's going to have to go to one of these things here. Now, because all of these elements share the same minimal polynomial, then it is the case that f adjoin alpha is isomorphic to f adjoin alpha zeta n. And in fact, I can put zeta n to the I there. Yeah, I'll just fix that up, that notation up there. So, this again is fundamental magic of Galois theory, that if you have two elements, in this case alpha and alpha zeta n to the power of I, one of these other roots of this polynomial, that share the same minimal polynomial, then if you adjoin each of them on, the field that you get is utterly isomorphic. They're algebraically equivalent. You're using different symbols, but that is where the difference ends. Apart from the fact that these elements are being denoted by different symbols, they are algebraically equivalent. And just using algebraic properties, if you were in this field versus this field, you can't actually tell the difference between the two. There's nothing you can do there's no difference between them. All that's different is the symbols that you have used, that they're isomorphic to one another. And that holds true for all of these. And what that implies, therefore, is that there is going to be an automorphism of f adjoin alpha, where alpha is mapped onto each one of these alpha zeta n to the I. So there will exist an automorphism of f adjoin alpha, which maps alpha onto each one of the equivalent things, because of the fact that these two fields are isomorphic. But these two fields are the same as well. They're more than isomorphic, because we've already shown that once you've got alpha zeta n to the I inside this field here. So these two fields, not only are they isomorphic, they're actually equal. How can I'm trying to think if I can draw a picture for this. So you've got this field here. So let's say here is the smaller field f, and then you adjoin on alpha, but you immediately, of course, get alpha zeta n here, and you also get all the other, alpha zeta n squared here. And when we're looking at this thing here, what you've done instead is you've adjoined on this element here, or one of them. So if we set I equal to 1, you've adjoined on this element here, but you still overall get the same field. So they are equal to one another, these two fields, but they're also isomorphic to one another, meaning that if you map alpha is equivalent to alpha zeta n, or alpha zeta n squared, or alpha zeta n to the I, and what that tells us is that there's going to be an isomorphism mapping between these two, where alpha is being mapped onto alpha zeta n, and that's going to correspond now to an automorphism, because they are equal. These isomorphisms are more than isomorphisms, they're automorphisms. So basically what we can conclude is here are the n automorphisms of the Galois group of K over F. I should have argued, actually, before we did this, why it is the case that this extension is a Galois extension at all. So why is the Kummer extension a Galois extension? Well, it's because it's the splitting field of a separable polynomial. How do I know it's separable? Because I've already shown you that it's got n distinct roots. So you might worry about this, because we're no longer assuming that the field is characteristic 0. So we no longer have the safety net of knowing that all splitting fields are Galois extensions. But in this case, we know actually that the polynomial definitely is separable, because I found its n distinct roots. So it is therefore the splitting field of a separable polynomial, and that's one of the equivalent definitions. There are 4 definitions that are all equivalent of a finite Galois extension, and being the splitting field of a separable polynomial is one of those equivalent definitions of being a finite Galois extension. So this extension is a finite Galois extension. What's its Galois group going to be? We've found all of the automorphisms now. Consider a special automorphism, the one which we'll call sigma, which maps alpha onto alpha zeta n to the 1. Then if you consider what sigma squared does, it's going to map alpha, it maps alpha onto alpha zeta n, and then it maps this again. Now zeta n is in the ground field, so zeta n will be fixed. Alpha will then be mapped onto alpha zeta n, so it's going to map alpha onto alpha zeta n squared, and then sigma cubed likewise is then going to map alpha onto alpha zeta n to the 3, and etc. So you see that the automorphism sigma actually is going to generate all the other ones. Sigma to the power of I is going to be the automorphism that maps alpha onto alpha zeta n I. So you get all the n automorphisms by taking powers of sigma, and therefore the Galois group of K over F is generated by sigma. It's the cyclic group generated by sigma, and that's going to have order n, so it's therefore going to be isomorphic to Cn. So that's therefore the proof that Kummer extensions are cyclic extensions. So we've started off, I think we'll have a break here, but I'll just summarise what we've done so far. So we've defined what a Kummer extension is. We've said that it is an extension that you produce by taking the splitting field over a ground field that contains a primitive nth root of unity of an irreducible polynomial of the form x to the n minus a, where a is in the ground field. And what we've shown so far is that that will have degree n, that it will be a Galois extension, and its Galois group will be cyclic, and therefore it's a cyclic extension. In part 2 of this video on Kummer extensions, we will look at how an equivalent definition of a Kummer extension is that if you start with a ground field that has a primitive nth root of unity, and you take a cyclic extension of degree n over that ground field, that immediately is going to be a Kummer extension. We'll show that it's a Kummer extension, and therefore that's an equivalent definition of a Kummer extension. We've shown that a Kummer extension satisfies that condition that we've just stated, i.e. it will be a cyclic extension of degree n over a ground field that contains a primitive nth root of unity. Now we're going to show the other direction, that if you are that we can conclude that you're a Kummer extension. Now, a little warning for the proof that we're about to do for that. It's a bit rabbit out of hat, some genius concocted the argument. Once I show you the bit of magic, the magic element that you have to consider, it's not too difficult to then follow the logic as to why it works, but concocting this magic element, it was done by some genius, and we're very grateful for that. So just to warn you that it is a bit rabbit out of hat, the proof that we're next going to do.